Oppenheimer did important research in theoretical astronomy, especially as related to general relativity and nuclear theory, nuclear physics, spectroscopy, and quantum field theory, including its extension into quantum electrodynamics. The formal mathematics of relativistic quantum mechanics also attracted his attention, although he doubted its validity. His work predicted many later finds, which include the neutron, meson and neutron star. Initially, his major interest was the theory of the continuous spectrum, and his first published paper, in 1926, concerned the quantum theory of molecular band spectra. He developed a method to carry out calculations of its transition probabilities. He calculated the photoelectric effect for hydrogen and X-rays, obtaining the absorption coefficient at the K-edge. His calculations accorded with observations of the X-ray absorption of the Sun, but not helium. Years later it was realized that the Sun was largely composed of hydrogen and that his calculations were correct. Oppenheimer made important contributions to the theory of cosmic ray showers and started work that eventually led to descriptions of quantum tunneling. In 1931, Heiko wrote a paper on the relativistic theory of the photoelectric effect with his student Harvey Hall, in which, based on empirical evidence, he correctly disputed Dirac's assertion that two of the energy levels of the hydrogen atom have the same energy. Subsequently, one of his doctoral students, Willis Lamb, determined that this was a consequence of what became known as the Lamb shift, for which Lamb was awarded the Nobel Prize in Physics in 1955. With his first doctoral student, Melba Phillips, Oppenheimer worked on calculations of artificial radioactivity under bombardment by deuterons. When Ernest Lawrence and Edwin Macmillan bombarded nuclei with deuterons, they found the results agreed closely with the predictions of George Gamow. But when higher energies and heavier nuclei were involved, the results did not conform to the theory. In 1935, Oppenheimer and Phillips worked out a theory, now known as the Oppenheimer-Phillips process, to explain the results. This theory is still in use today. As early as 1930, Oppenheimer wrote a paper that essentially predicted the existence of the positron. This was after a paper by Paul Dirac proposed that electrons could have both a positive charge and negative energy. Dirac's paper introduced an equation, known as the Dirac equation, that unified quantum mechanics, special relativity and the then new concept of electron spin, to explain the Zeeman effect. Oppenheimer, drawing on the body of experimental evidence, rejected the idea that the predicted positively charged electrons were protons. He argued that they would have to have the same mass as an electron, whereas experiments showed that protons were much heavier than electrons. 2 years later, Carl David Anderson discovered the positron, for which he received the 1936 Nobel Prize in Physics. In the late 1930s, Oppenheimer became interested in astrophysics, most likely through his friendship with Richard Tolman, resulting in a series of papers. In the first of these, a 1938 paper co-written with Robert Serber titled, On the Stability of Stellar Neutron Cores, Oppenheimer explored the properties of white dwarfs. This was followed by a paper co-written with one of his students, George Volkoff, on massive neutron cores, in which they demonstrated that there was a limit, the so-called Tolman-Oppenheimer-Volkoff limit, to the mass of stars beyond which they would not remain stable as neutron stars and would undergo gravitational collapse. In 1939, Oppenheimer and another of his students, Hartland Snyder, produced the paper, On Continued Gravitational Contraction, which predicted the existence of what are today known as black holes. After the Born-Oppenheimer approximation paper, These papers remain his most cited, and were key factors in the rejuvenation of astrophysical research in the United States in the 1950s. Mainly by John A. Wheeler. Oppenheimer's papers were considered difficult to understand even by the standards of the abstract topics he was expert in. He was fond of using elegant, if extremely complex, mathematical techniques to demonstrate physical principles, though he was sometimes criticized for making mathematical mistakes, presumably out of haste. His physics was good, said his student Snyder, but his arithmetic awful. After World War II, Oppenheimer published only 5 scientific papers, one of which was in biophysics, and none after 1950. Murray Gell-Mann, a later Nobelist who, as a visiting scientist, worked with him at the Institute for Advanced Study in 1951, offered this opinion. He didn't have Sitzfleisch, sitting flesh, when you sit on a chair. As far as I know, he never wrote a long paper or did a long calculation. Anything of that kind. He didn't have patience for that. His own work consisted of little abacus, but quite brilliant ones. But he inspired other people to do things, and his influence was fantastic.